Hey everybody, how are we doing? Today we are going to be diving into the combined gas law. But before we do that, I did want to do a quick reminder that Miss Teresa and I are missing y'all and hope to see y'all's faces again in the near future. Um, so let's dive on into these combined gas laws. Now, Miss Teresa has already talked to y'all a little bit about some of the properties of the gas laws and the main contributors to those gas laws and what they did. So let's kind of do a quick recap of those contributors. So we have Charles's law, and remember Charles described the relationship between volume and temperature. We have Boyle's law, who described the relationship between pressure and volume. And then we have Gay-Lussac's law, who showed the relationship between pressure and temperature. Okay. Now, if we combine all of those, we get what's called the combined gas law. Now, this does involve math. And so with this, we are constantly looking at the changes that are occurring in our pressure, volume, and temperature. Okay. Now, something to note. When we're doing this, your temperature does need to be in Kelvin. Every single time, your temperature needs to be in Kelvin. Okay? It has to be in Kelvin. Okay? If you're solving for it in Celsius, you're not going to get the right answer. So always make sure you convert into Kelvin. Now remember, for converting into Kelvin, Kelvin equals your degrees Celsius plus 273. Okay, so it's a very easy conversion, but it is something that you do have to remember to do every single time. All right. Now, we're also going to be working with pressure. An important thing to remember with pressure is that you need to be in the same unit. Okay, so every single time you need to be in the same unit. In making sure that you're in the same unit for pressure, if you've got your old periodic table that we gave you towards the beginning of the year, it is on there. Those conversions are on there. But if not, let's do a quick kind of look at what they are. So if I've got 1 atmosphere, that's going to equal 101.3 kPa, kilopascals, which is going to equal 760 mmHg, which is going to equal 760 torr. Okay, so if you look, torr and mmHg are the same thing. mmHg just stands for millimeters of mercury. Torr is the actual name for that. Okay, but either one of them are acceptable, so that's why we've got them both there. Okay, so you will need to make a conversion for that. So just keep that in mind when you're solving for your pressure if you notice that those pressures are in two different units. Okay, for volume, it's the same thing. You do need to make sure you're in the same unit. A lot of times the difference might be milliliters in one of the units and liters for the other. So you would just need to make that quick conversion to get them into the same unit. Okay. So here is our formula for the combined gas law. So our combined gas law is P1V1 over T1 equals P2V2 over T2. So we've got our first pressure, our first volume, and we divide that by our first temperature, and that's going to equal the second pressure times the second volume divided by the second temperature. Okay, so it's an easy plug in your numbers, cross multiply, and solve. Okay, now remember that your temperature must be in Kelvin. Again, I'm going to keep trying to emphasize that. Make sure that you are converting into Kelvin because a lot of times you're going to be given it in degrees Celsius. Why? Because thermometers measure in degrees Celsius. So we're going to need to make that conversion. Okay. Now, another thing to note is that I could be working in standard temperature and pressure. Okay, now this is a standard temperature and pressure. Okay, well, so what that means is that every single time I say that I'm at STP or standard temperature and pressure, it's always the same number. Okay, so standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. Okay, so this means again, 1 atmosphere would be your standard pressure or 0 degrees Celsius would be your standard temperature. Okay, Now, I might tell you that I'm in STP, and that's just going to remind you that that is those are the numbers that you're going to be looking for. Okay. All right. So here is our first problem. So it says I have a 3.5 centimeters cubed sample of nitrogen whose pressure is at 79.1 kPa, and it expands to 6.10 centimeters cubed, while its pressure also changes to 680 torr. At the expanded volume, the temperature of the gas is found to be 28 degrees Celsius. What was the original temperature in Celsius? Now, here's the thing. Again, your question is asking for Celsius, okay? Well, and they give you the problem in Celsius. So your initial response is to be, okay, well, I can just keep it in Celsius. No, you can't. Okay, you've got to remember you first, before you do anything else, you need to convert your Celsius into Kelvin. Okay, and then when you're all said and done, then you can convert it back into Celsius. Okay, so let's look at our numbers. I like to label the numbers. So it says I have a 3.5 centimeters cubed sample of nitrogen. Now, centimeters cubed is a measurement of volume. Okay, so we've got a volume right here, whose pressure is this, 79.1. There's pressure. And it expands to this new volume here. Okay, well, what that tells me, with it telling me that it's expanding, this is an action, right? So this is going to be my second volume. It's the volume when I'm done. This is going to be my initial volume, okay? So I've got V1 right here. I've got V2 over here. So now let's look at our other numbers. So again, here's my pressure, but it expanded. And then it says, while its pressure also changes to 680 torr. Okay, well, again, this is a pressure, but it says it changed to. So that again tells me that this is my pressure 2. Okay, and then that would make this my pressure 1. Okay, it says at the expanded volume, the temperature of the gas is found to be 28 degrees Celsius. Okay, here's our temperature. And that's at the expanded volume, okay? So that's my temperature 2. Okay, so let's look at our numbers and let's make sure everything matches up. So first, I've got volume right here and volume right here, okay? The one on the left is in centimeters cubed. The one on the right is also in centimeters cubed. So we'll keep them as they are. We don't have to change anything there, okay? Now let's check our pressure. So our pressure for pressure 1 is in kPa. Our pressure for pressure 2 is in torr. They're not the same unit, so we do need to make a conversion. It doesn't matter which one you pick, but you need to be consistent. They need to be the same, okay? So that is something we're going to have to change. All right, let's also look at our temperature. Okay, well, our temperature is 28 degrees Celsius here. Now that's in Celsius. So again, that's something I'm gonna have to change, because remember, your temperature has to be in Kelvin. Okay, so I have 2 big things that I'm gonna have to change before I can even start solving this problem. Okay, so first off, I need to get my pressures into the same unit. I personally like to work with the smaller unit. In this case, if you look back up here, which of these is smaller? Well, kPa is smaller. So I like to work with that. So I'm going to convert the torr, into our kPa. Okay, so let's do that conversion. So I have 680 torr, and I want to convert torr into kPa. Okay, well, my conversion is for every 101.3 kPa, I have 760 torr. Okay, so I'm going to type that into my calculator, and what I find is that I have 91 kPa. Okay, well, now I have my pressure 2. Okay, so this is pressure 2 now. Okay, another thing I need to do is convert my Celsius into Kelvin. So I'm going to take this and I'm going to add 273. Okay, well, what that converts this into is going to be 301 Kelvin. Okay, so now I've got my two new numbers. So this is my temperature 2. Okay. All right. Now, if you notice, again, we've got a change in our pressure, our volume, and or our temperature. Okay. With that change, again, that tells us that we're going to be using that combined gas law. Okay. So combined gas law is P1V1 over T1 equals P2V2 over T2. Okay. So now I need to plug in my numbers. So I had 79.1 as my P1 times V1. V1 was 3.5 divided by T1. Well, T1 is what I was solving for. So I'm going to put T1. Okay. And that's going to equal P2. Well, my pressure 2 was 680 torr, but remember we converted that back into 91 kPa times my volume 2. Well, my volume 2 was 6.10 divided by my temperature 2. Again, temperature 2 was 28 degrees Celsius, but I have to be in Kelvin, so we're going to put 301 right there. Okay. So now we've got our numbers. So now we just need to cross multiply. So these get all multiplied together, and then all of these get multiplied together. And what we're going to find is that we get 83331.85 equals 555.1 times my temperature 1. Okay, so now I'm solving for x. Okay, so divide both sides by 555.1, and that's going to give us 150. But again, remember that's Kelvin. Okay, so the next thing I would need to do, so my temperature 1 equals 150 Kelvin. So now I need to convert that back into Celsius. Okay, so let's look back up here. So if I originally wanted to convert from Celsius into Kelvin, I added 273. If I want to go from Kelvin back to Celsius, I need to subtract 273. So it's 150 minus 273, and we're going to end up with 123 negative, so negative 123 degrees Celsius. And that would be my answer. That would be the original temperature in Celsius before I did anything else. Okay? All right. So let's move on to this next one. So it says, what would be the volume? So I'm looking for volume of an 8.90 liter sample. Okay, again, that's a volume of gas at 100 degrees Celsius temperature and 113 kPa. Let's actually do this in a different color to make it a little easier for y'all to see. Okay, so we'll do that. So I have, again, this volume, this temperature, this pressure. If the conditions were changed to STP, okay, again, so right there, they're telling us two pieces of information. They're telling us our temperature and they're telling us our pressure. Well, our temperature at STP is 0 degrees Celsius, okay, or 273 Kelvin. Again, you need to solve in Kelvin, so you might as well go ahead and use that number. So this is 273 Kelvin. And then my standard pressure is 1 atmosphere, okay? Well, 1 atmosphere is also equal to 101.3 kPa. And since my other one is also in kPa, so why don't we just keep that? So 101.3 kPa. Okay. Now it tells us that the conditions were changed to this. Okay. So what that tells me is that this is my temperature 2 and this is my pressure 2. Okay. And then they ask me what would be the volume. Well, so that would tell me that the volume 2. All right. So I have volume 1, temperature 1, and pressure 1. Okay. Now again, this is going to be a change in pressure, temperature, volume. So what that tells me is it is combined gas law. So P1V1 over T1 equals P2V2 over T2. And I just plug in my numbers. So my pressure 1 was 113 kPa. My volume 1 was 8.90 divided by my temperature 1. Now, one thing that I did not do yet is convert that into Kelvin. So I do need to do that before I can solve this problem. This is in Celsius, so let's go ahead and convert it into Kelvin, which remember is just plus 273. Okay, so 100 plus 273 gives us 373 Kelvin. Okay, so that's what's going to go right here, 373 Kelvin. Okay, now that's going to equal my pressure 2, which was at standard pressure, so 101.3, times my volume 2, which I'm solving for, divided by my temperature 2, which was 273. Cross multiply. So these get multiplied together, and these get multiplied together. Okay. Plug that in your calculator. What you'll find is that you get 274,556.1 equals 37784.9 times my volume 2. Solve for x. Divide both sides by that 37,784.9. And what you're going to end up with is 7.27 liters as your answer. So your volume 2 equals 7.27. And that would be our answer. If the question asked for milliliters, you would just go ahead and multiply that by 1,000. Okay? All right. New color. So what happens to a volume of gas if its pressure is tripled and its temperature in Kelvin is doubled? Okay. So if your pressure is tripled and your temperature is doubled. All right. So here's how we do this. So this is a combined gas law problem because, again, we're changing our pressure, volume, temperature, those things. So P1V1 over T1 equals P2V2 over T2. Okay? So what happens to the volume? That means I'm solving for my volume. Okay? All right, so let's plug in numbers. Well, what numbers do I use? Well, for pressure 1, it's going to be the original value. So 1. For volume 1, same thing, original value, 1 value. And temperature 1, original value, so 1. So everything over here on the left is going to be 1 because it's all the original value, okay? Your pressure was tripled, so 3 times 1 is 3. Your volume is what we're solving for, so volume 2. And your temperature was doubled. So 2 times 1 is 2. Okay, and then we just solve it like we would any other problem. So cross multiply. So we get 3v2 equals 2. And if we're solving for that, we find our volume 2 is 2 over 3. Okay, so what does that tell me? Well, it tells me that the volume would decrease by 2/3. Okay, so that tells me my volume is going to decrease by 2/3 because when we solved it, we got 2/3 as our answer. Okay, so here is the answer to that problem. Okay, all right. So, looking at our next problem. So it says a gas has a pressure of 1.45 atmospheres when the temperature is at 80 degrees Celsius. Okay, so this is a pressure, and this is a temperature. Again, we're going to need to convert that into Kelvin. We'll do that in a second. What would be its pressure if the temperature is changed to 35 degrees Celsius, okay, and they said the temperature is changed, so this is temperature 2. They also say what would happen to the pressure if that happened. So that's my pressure 2, okay? If the gas is confined in a rigid container. Now, rigid means that the volume is not going to change, okay? So that's just reiterated right there, where it's to a rigid container where the volume will not change. All right, so that means this is my pressure 1 and this is my temperature 1. Okay, so if you look at this, your volume isn't there, right? We don't have those numbers. But we do see that our pressure and our temperature are changing, right? So we still use the combined gas law. So P1V1 over T1 equals P2V2 over T2. Okay, but they don't tell us our volume. So what do we do with that? Well, what we do is that since our volume doesn't change, it doesn't matter. It can come out of here, okay? So really, our equation is P1 over T1 equals P2 over T2. Okay, now we plug in our numbers. Okay, before we do that though, again, we should be converting our degrees Celsius into Kelvin. So 80 plus 273 gives us 353. So plus 273 gives us 353. And 35 plus 273, so this plus 273 gives us 308. Okay, and then we plug in our numbers. These are Kelvin. Okay, so I plug in our numbers. So P1 was 1.45 atmospheres. 1.45 divided by T1, which we found to be 353, equals P2, which was what we're looking for, divided by T2, which was 308. Okay, so we plug in our numbers. What we'll find is that we get 353 P2 equals 446.6. Solve for x, so P2. Okay, divide both sides by 353, and you'll find that your P2 equals 1.27 atmospheres. Okay, now again, we didn't know our unit, but we did know that when we solved the problem, our initial pressure was in atmospheres, so we're going to keep it in atmospheres. Okay, so it's 1.27 atmospheres. So that would be my answer. Okay. All right. Moving on, 2 more problems. So if a gas is known to have a pressure of 200 kPa after it has been heated, so here's your pressure. After it's been heated to 65 degrees Celsius, so temperature, what was the beginning Celsius temperature? So temperature, and it says beginning, so that's temperature 1. If its pressure was originally 750 mmHg, so this is pressure 1. So that makes this pressure 2 and this temperature 2. Okay, first thing is to convert those temperatures into Kelvin. All right, so 65 plus 273. And what we're going to end up with is 338 Kelvin. All right, our pressures, if you notice, are not in the same unit. So again, I'm going to have to convert them into the same unit. I personally like the smaller unit. So I have kPa, I have mmHg, kPa is the smaller unit. So let's convert that mmHg. So 750 mmHg, convert that into kPa. And our conversion is for every 101.3 kPa, we have 760 mmHg. So I typed that into my calculator, and I'm going to end up with like 99.96 something, something, something. Okay. Well, I need 2 sig figs, right? So that rounds up to 100. But with 2 sig figs for 100, it's 1.0 times 10 to the second kPa. Okay, so that would be our pressure 1 that we're going to be working with. Okay, all right. So now, again, we've got our change in pressure, our change in temperature. That's what's changing. So we're going to need to use our combined gas law. Again, I like to write it out every single time. It reminds me of what I'm doing. P1 V1 over T1 equals P2 V2 over T2. Okay. Now, again, looking at our problem, it doesn't have anything to do with volume. All it says is that the volume is constant. If our volume's constant, again, that tells you that the volume isn't going to affect anything. It doesn't matter here. So we can cancel out that unit. So P1 over T1 equals P2 over T2. Okay. So I need to solve it. So I'll plug in my numbers. So my pressure 1, which after I converted it is 101 or is 1.0 times 10 to the second divided by my temperature 1, which is what I'm looking for. So temperature 1, that's going to equal my pressure 2, which they told me was 200 kPa, divided by my temperature 2, which was 338, and we cross multiply. That and that. Okay, and what you find is that you get 33,800 equals 200 times T1. Solve for X. 200 or 33,800 divided by 200, and you're going to end up with 169 Kelvin is your temperature 1. But my question asks for it in Celsius. So I do need to remember to convert that into Celsius. And remember, converting that into Celsius means to subtract 273, which is going to give us a total of negative 104 degrees Celsius. So this would be our answer, 104 degrees Celsius. Okay. Very last problem here on the combined gas laws. So let's take a look at it. So it says, to what temperature in Celsius must a gas at 50 degrees Celsius, so this is my temperature, I'm going to need to convert, and 107 kPa, that's a pressure, be heated in order to increase its pressure to this, 3.50 atmospheres, if the volume remains constant. Again, our volume is remaining constant. So that's going to tell you that you don't need to have it in your combined gas law equation. Okay, so what temperature must a gas at 50 degrees and 107 kPa be heated in order to increase its pressure? So we want to know, what is the temperature to? So that's temperature 1, because they tell me that this is increasing it to 3.50. So my pressure 2. And then this would be my pressure 1. All right. So before I do anything else, let's make sure everything's in the right unit. First off, my temperature 1, if you notice, is 50 degrees Celsius. We need to convert that into Kelvin, which means we need to add 273. So we're going to get 323 Kelvin. Okay. Now, again, let's look at our pressures. We have pressure 1, which is in kPa, and pressure 2, which is in atmospheres. I like to convert to the smaller unit. Smaller unit here would be atmospheres. So for converting into atmospheres, I take this kPa, so 107 kPa, and I go from kPa into atmospheres, and there's 1 atmosphere for every 101.3 kPa. Plug that into your calculator, you're going to end up with 1.06 atmospheres. Okay, so my initial pressure was 1.06 atmospheres. Okay. Now, I need to solve it. Now, again, we do have a change in pressure and temperature. So we're going to use our combined gas law. P1 V1 over T1 equals P2 V2 over T2. Volume is staying constant, so we can get rid of that unit. Now we plug in our numbers. P1 was 1.06 atmospheres over T1, which we found to be 323 Kelvin, equals P2, which was 3.50 atmospheres, over T2, which is what we're solving for. And we're going to cross multiply. Okay, so we get 3.50 times 323. That's going to give you 1130.5. And that equals 1.06 times my temperature 2. Okay, solve for x. So divide both sides by 1.06, and you'll find that your temperature 2 equals 1066.5. All right, so we got 1066.5. Let's check our sig figs. Okay, we need to have 3 sig figs, which converts this into 1070 Kelvin. But again, my question asks for Celsius, so minus 273, which is going to give us a total of 797 degrees Celsius. All right, y'all, so that is it for our notes on the combined gas laws. All right, y'all, so that is it for your notes on the combined gas laws. I know it was a math-heavy unit here, or this topic was a math-heavy, but y'all powered on through it. Remember to, don't forget to ask if you've got any questions. Miss Teresa and I are always hoping to answer your questions and fill in any gaps you have. And yeah, just let us know if you need anything.